Welcome to um, uh, Hi everyone. Welcome to our challenging summary. We will investigate all the participants give our pre-attention about their methods, how they got their results. We investigated the top seven participants give our presentation according the list. So we will investigate the general cohort give our presentation. Are you ready?
Yes, I can.
I will. You can you can share your screen with other people's.
Yeah, 1 second. Let me share the right screen here. This. Can you see the browser?
Yeah.
All right. And I hope now you can see the full screen. Can you see the full screen now?
Yes.
All right. Okay, so I'm gonna present our approach to this challenge today. I guess I don't have to go over the details too much, but just maybe small recap. So we're trying to segment the fetal head and the pubic symphysis from 2D ultrasound images. And of course, from these, the goal is then to sort of estimate the angle of progression. And this kind of, this measurement can guide whether or not forceps or mentors should be applied during birth. So this is quite a nice task, I would say. And so a little bit about the challenge data. So we had 4,000 images, which are fully annotated with both classes. And we found that it looks like the data comes from somewhere around 400 to 700 unique scan sessions. I'm not sure. Maybe the organizers can share this if that's if the ballpark is correct here. And of course, from each scan session, there can be a lot of images generated. Yes, and also we were wondering, because in our cross validation, we saw quite a strong dice performance, which was not as strong on the leaderboards. So we were wondering if maybe this could be the source of this discrepancy, because if in our folds, we didn't sort of account for the multiple scans being from a single session. And of course, this can lead to some kind of information leakage, which can sort of skew the results to look better than they are, but maybe we'll see. And anyway, for the validation and test phase, or phase 1 and 2, there were more images. Okay. In our approach, we kind of built on an unit or used it with some small changes. but in general, I guess the community usually knows how or what NN unit is designed to do, but it's like basically a segmentation method which is open source, and it basically can sort of adapt the whole pre-processing and data pipeline, data augmentation, architecture, etc., to some given segmentation problem. And so this was also coming from our group. This was kind of a natural choice. Yeah, and to sort of comply with NN unit's data format, we had to first convert the MHA images to PNG because this is basically due to the way IO classes in NN unit are implemented, and at the time of this challenge, only PNGs supported 3-channel inputs, and the challenge data was in 3-channel inputs. Maybe one could have also just reduced it to 1 channel, since I think they were just copies. Okay, and then for this, we use simple ITKs, like read and write image is pretty straightforward. And then moving the images to the respective folders, and then basically go over the standard process of NN unit, like generating the dataset JSON and pre-processing, etc. Okay, in our the kind of variations we tried in NN unit is maybe for some context. NN unit tries to configure the architecture like to some target GPU memory during training. And since NN unit was released, I think by now a few years ago, yes, the target memory is not sort of up to date to like current hardware. So basically, in version 2 of NN unit, one can also set the target memory size higher. So that's kind of what we did, which basically leads to, among others, a larger batch size. And then variations we also tried was using additional losses based on out-of distance, and one which is sort of an implementation of a focal loss. And in terms of network architecture, there's also an option to implement a residual encoder, which we also use, and I think was present in the final submission. And also what we tried was stronger data augmentation, which led to I think it led to some improvements on the cross-validation, but it's unclear whether that translates to the leaderboard. All right. So these are our kind of cross-validation results. So you see the default is like really the NN unit default, the smaller batch sizes, and then you can see like adding the focal losses, residual encoder, larger batch size, and stronger data augmentation. And as you can see, there's some gain in the dice scores and out-of distance, but yeah, as I said, this is a 5-fold validation, and it's unclear if that translates well. Okay. Now for our final submissions, this is like in red. You can see what we used as the first submission, basically, which is just the default NN unit and applied some stronger data augmentation. And in the second, what I also should mention is that, like, also in this submission, what we use as the final submission is an ensemble of the 5 folds we used basically for cross-validation. And in the second submission, we basically used a larger ensemble, which was based on the individual folds of these three methods. So again, the default plus stronger data augmentation, then the residual encoder with stronger data augmentation and the focal loss, and also one without the focal loss. And this second submission, however, scored a bit lower, I think, in the final leaderboard. Yes. Oh, yeah. The sources basically, I mean, you can GitHub, NNUnit is open source on GitHub, so I guess everybody can reach it. And we also provided the code which we used for this challenge. Yes, and I think with that, I would be at the end of my presentation. I hope I didn't stretch the time too much. Thank you.
Okay. Do you have any question about this presentation? Is there any question about the fourth player? Okay, I have one question. You use the NNUnit, but this model is very large. Yeah. Can you tell me how many parameters of this model, and how many times you train that one epoch?
So I'm not sure about the second question, but if I understood correctly, the first one. So the number of parameters I would have to look up. It's I can see it in our logs, but I don't have that on the slides, unfortunately. But I can maybe in the course of this session look it up and post it for everybody. And I'm not sure what the second question about inference speed. Did I get that correct?
Yeah. Inference speech. Yeah.
Okay. So what NNUnit usually does during prediction, because it comes from sort of like 3D segmentation problems where often you don't get a full scan in basically in the input size of the unit used. So what it then does is sort of a tiled prediction. But in the case of like 2D images, this is not really required because it's the memory demands aren't as high naturally in this 2D domain. So I think the actual inference, if using CPU, is it's fast. So I think the pre-processing the image is can be regarded as maybe the longer part of the pipeline than the inference, or maybe not quite. Depends on how strong of a data augmentation one uses at test time. But yeah, it was really quick, much quicker than one is used to from the 3D domain.
Okay. Another question about the hardware you use that.
Can you repeat that? I didn't get that.
Maybe some people use 3090 or some hardware you use that. What kind of the hardware you use that?
Which kind of hardware? Okay. So we use different. So initially, the NNUnit default just is basically targeted at some GPU memory around 9 GB. So I think this is like not even previous generation, but before that. But if we scale it up basically to a larger batch size, we try to set the target memory to, I think it was somewhere around 22 GB So yeah, it ran on some, I'm not sure since we have different hardware in our cluster, but I think it was some V100s which match that. And of course, the current generation A100 has already more than is required. So there's even room to scale it up also with data parallel, but I don't think that this is necessary or beneficial in this task, right? I think there are other parts where one can see more gains, or maybe this becomes relevant if there's like more data available. One would have to see. But
Okay.
yes, so for the largest models, I think it was around 22 gigabyte video memory.
Okay. Thank you. Is there any question about this presenter?
I have a question.
Okay.
Oh, yeah.
Do you use the test data augmentation in your inference?
Yes, we did in like the default NN unit setting. So I think this, if I remember correctly, it only does some mirroring, but not.
Oh, okay, I know. I'm also a user of UNet, and I think it's very wonderful.
Yeah. Yeah. Okay. So I hope this answers your question.
Thank you.
Thank you.
Okay, we will save the time and investigate the running app participant give us presentation. He gets the, I think he gets the best result about the segmentation this pad, but he do not get the best score according our rules. So I will investigate the Mavan Kafa give us the presentation. Yeah. Okay.
Hello, how are you doing? Everything. So let me start presenting.
Can you make the loud more loud? We can hear you. We can't hear you.
Can you hear me? Hello.
Okay.
Hello, can you hear me?
Okay.
Yes.
Very good. Clear.
Super. So thank you, Gregor, for your presentation. My name is Marwan, and I'm going to present you our work or our submission for this challenge. Our team name is Aloha, which means hi in Hawaiian. So to start with, the angle of progression estimation, as the first participant mentioned, it's used in measuring the fetal head descent in the second stage of labor, which in fact correlates with the mode of delivery, whether it's vaginal or C-section. And over this data set and this task in general, you can see that there are positional priors that someone can leverage in a way. So if you visualize the probabilistic atlas, or in other words, the probability that every pixel belongs to a class, you can notice that the fetal head object over this task, over this data set, are mostly centered around in the middle of the image. While when it comes to the pubic symphysis, it's more like top-centered in a very precise place. So it makes sense that while we are doing our data augmentations, we don't use vertical flipping, because such variations we will not see over the training or over the test set. So in fact, if you use vertical flipping, in my case, was not helping the model in a manner. This was our first takeoff. The second one is that how can we use these priors in general in segmentation models? There is a lot of ways that you can use them, but in our submission, we wanted to explore the state-of-the-art segmentation model, like the segment anything model, and see how can prompt tuning can encode these positional priors and come up with an accurate segmentation. So this is our framework for the training in general. But to start with, we divided the data set across 5-fold with prior similarity splitting, because as Gregor mentioned also, if you divided the data set randomly, it will have some sort of data leakage over your validation set, and that can explain the higher validation score that Gregor was achieving. So if you noticed over the data set and went through it, you can see that, in fact, it's ordered by the patients. So we did some prior similarity splitting to generate the 5 folds. And based on that, we trained SAM. Specifically, we trained the prompt encoder and the default prompt to capture or to leverage the positional priors that are available for this task, knowing that the head is centered in the middle and the pubic symphysis is centered in the top center of the image. So this prompt encoder can actually encode such information. Also, we fine-tuned the full mask decoder, and full fine-tuning of the mask decoder is beneficial to kind of capture the contextual information coming from the image encoder. And for the image encoder, because most of us for sure know that the segment anything model have a lot of parameters. So full fine-tuning of this big model can suffer from over-parameterization, no? And also extreme overfitting. So we adapt a low-rank fine-tuning strategy, namely LoRa. And this LoRa just simply proposed that instead of fully fine-tuning your whole model, you just add the gradient through a low matrix decomposition. And it's being compact, being 1% of the overall image encoder. Also, our strategy or our motivation to fine-tune the image encoder with adapters comes from the idea that ultrasound imaging is not present in the pre-training dataset of SAM, or the segment anything model. Ultrasound dataset, I believe, have its own unique characteristics, like the high frequency speckle noise, for example, that SAM is actually sensitive to these frequencies over the natural images, because if you want to segment an object over the natural images, you would focus more on the edges or the high frequencies. But if you focus on the ultrasound imaging over the high frequencies, you will actually be like not converging to your task, given that ultrasound imaging suffer from this high frequency speckle noise. And after training with 5-fold, we do the inference with test time augmentation by flipping the image only horizontally, as I previously mentioned, because we didn't use the vertical flipping augmentation. And by flipping the image and using the 5 compact trained LoRa models, we can generate 10 predictions, and then we average these predictions based on soft ensembles to give the final output. And for sure, as a post-processing, we keep the largest component, bearing in mind that we only have 2 components, like 1 fetal and 1 pubic symphysis. The results over the segmentation, as the organizer mentioned, were nice, not over the angle of progression. And I would like to really congratulate the first people that got the lowest angle of progression error. And yeah, I won't discuss again, to be honest, the score discrepancy. For future work, I would say it's better to do some sort of thresholding for pubic symphysis to avoid missing predictions. We don't have any prior how these missing predictions are being handled in the evaluation step. For example, if you missed a pubic symphysis, how the angle of progression is going to be estimated. Or if you only have 1 or 2 pixels over your pubic symphysis, fitting the ellipse over this image will actually throw an error. And would you actually put the missing prediction as the highest 180 angle, or would you put it something in the middle like 90, given that you have already a reference of the pubic symphysis over your target task? Also, minimizing the angle of progression lost through SAM was not beneficial, mainly because the angle of progression is coming from the segmentation labels, or the segmentation or the annotations. And these annotations are subject to bias in certain radiologists. So when you propagate this to the angle of progression, in fact, you are not helping the model, but you are helping the model to leverage the bias of the segmentation. So I believe that for future work, the predicting the angle of progression reference point can be beneficial. Also, with a ground truth for the angle of progression reference points can provide a more sophisticated models. And for sure, shape-aware losses can benefit all of these. And that's it. Thank you, Aloha team from here, from Hong Kong. And certainly I will be in MICCAI next week. So if any of you gonna be there and have any question or would like to discuss face-to-face, I would be more than happy to discuss with them. Thank you.
Is there any question?
Hi, hello, hi, this is Fan. I'm Marvin. Thanks for the presentation. It's quite interesting. I just want to ask you about something about LoRa. Because I was working on the LoRa for medical image as well. So in your framework, I want to ask the default prompt and the prompt encoder. So for the training data set, how do you define how did you define the default prompt and also the prompt encoder? So can you show some details of like how did you do the fine tuning on the prompt encoder?
Super. For the default prompt and the prompt encoder, it's actually, I would say it's a learnable parameter. So this default prompt is a learnable vector that you can give to the prompt encoder. Mentioned it's the prompt embedding. So by learning both of them, you kind of lose the benefit of prompting SAM with points or bounding boxes, because you learned a default prompt over your task and you cannot interpret this prompt in a way. But you can definitely learn the prompt encoder, the default prompt, with simple training, I would say. Like, so it's like parameters.
Okay, so is that being you're using some pre-trained model to do the training to do the fine tuning on the prompt?
Fine tuning on the prompt? No, I didn't use any pre-trained model. In fact, we tried a lot of ways, like with the LoRa, like we tried GLoRa, we tried FACT, we tried a lot of adapters, and we find that actually LoRa was performing the best. So we used it in our task. But for this manner, we just trained the full prompt encoder and the full prompt in a normal manner, similar to the yeah, I will kind of share with you the GitHub later for SAM with LoRa. It was published at the beginning of this month, year, and they trained the prompt encoder and the full prompt normally, as if they are NM parameters, you know.
Okay. Okay. I have one more question. Is for the training data, because this is ultrasound image. How did you how do you say how did you set up the prompt for each image? Or did you do that, or you do that different way?
No, in fact, this default prompt is converged to a global prompt over your target task, over your target data set. So you don't switch between prompts. There is in literature for sure that you have prompt tuning for this, and not only one, but for example, you can learn 10 of them and choose the one that best suits your image. This can be like further exploration, I'd say.
Oh, okay, I got it. Thanks, thank you.
Of course.
Is there any question?
Yes, and have a small one, because my first question would also have been about the prompt, so this is already answered. Yeah, first of all, thank you for this nice presentation, and I really like your approach. I was wondering, so the prompt encoder, mask decoder, and LoRa layers of the encoder, they are all trained together, right? Or is there some different stages to it?
We train them end to end. Yeah, all of them are trained together.
Okay.
Yeah.
Yeah, that would also already be my question. Everything else was already answered. Again, congrats on this nice approach.
Thank you.
Any question? Okay, I have one question.
Yep.
First of all, I should tell you, in our previous studies, we get some conclusions. If we get the good result about the FHPS segmentation is good, but we can't reproduce good the angle or progression. So in our studies, we get the conclusions maybe not we get the good results can get the good performance of the measurements. So this part I can explain why you do not get the best score.
No.
Maybe this is our limitation about this challenging. I think in the further we will improve this part.
Yeah,
But
I don't
you
have any
also
problem.
the good attention and the most good methods for the segmentation task. Yeah.
I actually don't have any problem. Like, I'm really like, I don't have any problem. But I would just appreciate that a reply can be comprehensive, like asking my questions or concerns related to the challenge. Like for me, the second two digits all over all the scores are insignificant. It means like maybe I can be fifth, like not even second. And for me, this is kind of unfair. Maybe like I can be fifth or sixth, like I don't know. But in general, as you previously mentioned, it has some limitations for sure. And we would like to congratulate really the winners because they had like the least angle of progression. And I believe this is the downstream task for this challenge. And yeah, for sure, like that's it. Thank you.
Okay. Next one.
Hello, can you see my materials?
Yes.
Okay, this is Qiu Yaoyang from China Medical System China, and our topic is neighborhood weighted dice loss for better segmentation boundary. And I will introduce in these 4 parts. And the first is the background. These are this part is basically consistent with what the previous speakers have discussed, so I skipped it directly. And the next part is the method we used. And in the pre-processing stuff, the only point worth mentioning is that we normalized the input data using the mean and the variance of areas with images greater than 0. And considering the effective region in the ultrasound image is a sector, so it has much meaningless black padding, and the distribution of all pixels is obviously different from the true distribution of the effective values. So, and the shape of the effective region is not fixed. And there are few points with pixel values of 0 within the region. So we use pixels bigger than 0 in the image to approximate the true distribution. And others in this step are similar like others. The network we used is ARPANET. We believed that the boundary smoothness and the uniform size of the segmentation target led to the low difficulty in feature extraction. So this network has no any structural changes. And this figure shows the structure. And the key point of our method is the loss we used. In our experiment, we found that existing methods usually led to classification errors on the boundary area, which is the main problem of AOP error, and you can see this. So we can use weight to help the model to pay more attention to this area. And here is a method. Distance map loss generates the weight map by calculating the Euclidean distance map corresponding to the mask to increase boundary weight. But this method does not consider the influence of boundary shape and the weight at all boundaries are at their maximum values, and the weight of pixels farther away from the boundary in the distance map decreased. But in the convolutional neural network, the receptive field of a single point is always limited. So considering this, we introduced the neighborhood weighted dice loss. And the calculated way is for each pixel point on the image, we define its I neighborhood as a square area centered on the pixel and have a fixed side length, and calculate the proportion of points in the area that are different from that point, which is the I neighborhood weight for the point. And to consider the boundary in the different receptive field, sum the neighborhood weight map from 1 to gamma to get the final neighborhood weight map. And gamma is a hyperparameter set to the number of downsampling times of the network, which is 5 here. Finally, to avoid situations where the weight is 0 and increase the attention to small objects, the final weight map needs to be added with 1 and class with C. And this is the weight map we calculate. And you can see that our method generates greater weight at sharp points than at smooth points, like here. And there is no longer a weight difference at points far away from the boundary. You can see at here the weight is almost the same. And for the final n-dice loss, the equation is here. Next is our experiments and the results. We test our method on the training set, which contains 4,000 images, and we randomly select 8 cases as the test set, and use the rest of for training the model. And the model structure is ARPANET without change, and the backbone is ResNet. All our experiments are conducted using segmentation, and our evaluation metrics including dice and score without AOP. And we can find in our offline evaluation, the n-dice loss get the best results. And to further enhance the generalization ability of the model, the final submitted model was trained using all 4,000 images from the training set. In summary, our method shows a more reasonable boundary weighting way and helped to better accuracy in this challenge. And this method is simple to implement, can be extended to other convolutional-based segmentation models. And there is still room for improvement in the experiments, for example, by adding test data augmentation or integrating the results of multiple models to further enhance the generalization ability and reduce the inconsistency between local and online evaluation. And we have found some issues with the label of the dataset, which remains unchanged when there is a slight shift in the image on consecutive frames. So it is still was considering how to adjust this issue. That's all. Thank you. Do you have any questions?
Good presentation. Is there any question? Okay. I have a question. I think you also you have say this original figures. Most of the figures there's no bundle or no this region for segmentations fetal head or PS. So do you think the low resolution image has influence on your methods, or some paths. Can you explain this path, or based on your results or your experiments, can you explain this issue? Yeah, can you hear me?
Yes, but
I repeated the question. Because we know all data set, there are many figures. They do not have the clear boundaries or the edges. Under these conditions, can you comment your methods on this task?
How to calculate the boundary weight? That.
Yeah.
The boundary are all defined by the label. So, yeah, if not. Sorry, I want to use Chinese.
Okay.
My English 就是它这个模糊边界，在这个任务里面是没有被定义的，就是我这个边界全部都是通过 label 来算的 ，label 的边界怎么定义？是根据它这个来划区域，所以因为它的边界模糊，导致它这个更难区分的话，其实你只要 label 标准就可以了，就是我这个边界区域标准了，比如说在这我现在没有共享屏幕。就比如说在这个图里面的这个边界，它虽然是模糊的，但是只要它的 label 标出了这个区域，那么这个 boundary weight 就可以让模型去关注这一部分。就从这个图里面算出来，意思就是这个边界的这一部分区域都会被它重点关注，所以它的边界在这里有模糊，比如说可能往里的一点，往外的一点都不会有。
OK。你的意思呢，就是说，如果在原始图像里边，如果它那个边界是准确的，然后是正确的，你这种方法是非常有效的，对吧？因为你看你的这个里边的这一张图，就是说 methods 这张图，第6页的这个 slicer，不是，对，你看，实际上我们这个地方标的是有问题的，你看它不是已经超出去了吗？就是第一幅图，看到没？它那个斜的那块出去的那块呢，相当于是我们是为了计算那个 AOP，它相当于是一个椭圆的那样的一个形状。但是它在成像或者说它在获取这个图像的时候，并没有把那个原始的这一侧的那个整上去。你可以认为呢，就是说实际上我们在超出去的这一块的，它那个label 呢，相当于是有问题的。
这个应该不是在我这个方法的，我方法主要解决的不是这个问题，就这个假 label， 它应该还是根据这个 label 整体的连贯性来算的。
OK. Is there any question? No question. We will investigate another presentation. I think another one is not here, but he gave us a video about his presentation. I will share it with us. Wait a few minutes. Next one is公平层, yeah.
Hear me? Hello?
Okay. We can hear you.
Okay. Hello everyone. My name is Gong Ping from the School of Artificial Intelligence of MICCAI University. Now I'm a PD student. My leader is Professor Dai Yu. Currently, my main research is medical imaging analysis and deep learning. As part especially the processing of medical ultrasound images. I would like to thank the organizers very much for giving us an opportunity to communicate and learn. The following is the introduction of our proposed method in this challenge. The first is the start motivation. As we all know, since the emergency of UNITE, it and its variant has been widely studied on various segmentation tasks, especially on medical imaging analysis. Figure 1 shows the 4 types of variant based on UNITE on segmentation tasks, such as the multi-scale variant, the attention variant, the deep supervision variant, and their hybrid variant. It is well known that a proposed same model should take into account of 4 properties shown in figure 2. The four properties of efficiency, robustness, and complexity and generalization. Through the study for this variant, we have drawn 3 simple conclusions. The first, the most methods are designed based on the single or specific task and rarely balance the robustness and generalization. Therefore, the robustness and generalization of ultrasound imaging of this network need to be further improved. Second, the complexity of this network has not been adequately considered. In Figure 3, we demonstrate the complexity and size of 19 variants. As in Figure 3, all these variants significantly increase the computational cost compared to the original UNITE. Third, the ability of the benchmark network to characterize the medical ultrasound imaging was not sufficiently dissected, such as depth, kernel size. Although UNITE Plus asserts that we can use a cellular U-shaped network to obtain the same network performance, this conclusion has not been confirmed in medical ultrasound imaging segmentation tasks. As we all know, increasing the kernel size is sometimes equivalent to increase the network depth, but increase the network depth has less computational overhead. Therefore, we only explore the effect of the network depth on ultrasound. Figure 4 illustrates the network with different depths. The Figure 5 demonstrates the segmentation result on 2 public breast ultrasound datacities. It can be seen from Figure 5 that peer-richly increase the network depth can significantly improve the segmentation accuracy of medical ultrasounds compared to the original UNITE. In addition, the result on the 2 ultrasound datacities, KUS and KCUS, also demonstrates the necessity of increasing the network depth. The more analysis about the performance of the baseline network is available in our work, published in partner contribution. Although the simply increase the depth of the network has greatly mitigated the occurrence of misdetection and false detection as shown in Figure 6. However, due to the complexity of ultrasound images, these segmentation results still need to be further refined. In order to obtain the more refined segmentation result, we developed a new network named the DSE UNITE. To balance the complexity of the network, we only introduce SE block and set up the deep supervision in the 15-layer UNITE. In summary, there is no particularly innovative work in DSE UNITE, which mainly aim to achieve the more efficient ultrasound segmentation using the simple strategies. It can be seen from the Figure 3 that although our approaches have the more network parameters, it does not significantly increase the computation overhead. To further validate the effectiveness of these campaigns, we performed the evaluation experiments on the public breast ultrasound and the kidney ultrasound respectively. The experimental result shows that the introduction of these components can gradually help the network to obtain the best segmentation performance. The more detail about DSUNet can be found in our published work. Finally, the DSE unit is applied to the challenge and achieves the fifth result. This is a brief description of our level. If you are interested in our work on medical ultrasound, you can scan the QR code to get more detailed information. We will also welcome you to visit us. The above is my content of my speech. Thank you.
Is there any question? No. So I have a question. Because in your presentation or in your slides, there is no result about all data side. Can you explain why, or just give some explain or comment? Yeah.
当然是我们说中文吧。
OK。
我没有太听明白你刚才问的问题是什么。
我的意思是说，您的这个结果里边，这个要不然我的意思是说，没有关于我们数据集的结果。
这个因为我只来了一个最终的排名，因为这个它没有，因为在这个工作中呢，就是没有具体的进行一个超参上的优化，所以说可能结果排名也不是那么理想。
OK。我想问一下，就是说您上传的这个代码好像，能重现你的结果吗？
可以的，可以的。
OK。
这个是没有任何的这个loss function 的一个优化的，所以呢是直接就是 DSE loss， 所以说就很简单。对于这些第三方人员来训练的话是极其简单的。
OK。我没有更多的问题了，我看一下其他人还有没有问题。Is there any question about his methods? No. Okay. Next one.
Hello everyone. Can you see my screen?
Yeah.
Okay. Hi. Thank you, Dr. Bai, for organizing this challenge. And this was quite interesting challenge for me. My name is Fang Yijie. I come from University College Dublin in Ireland, and my supervisor is Guluni and Dr. Guluni and Dr. Kathleen. My research topic is efficient lightweight deep learning models for fetal ultrasound images on edge computing. About this challenge, I would start with my network, and we're talking about some data augmentation and loss function, and then I will show some results with my method. I will skip the introduction. So about our network, we are using the UNet, so the UNet is very popular in medical images. So we design a baseline UNet, but we did modification on the baseline UNet. We think about to replace the encoder of the UNet because our previous research was fine-tuning the UNet, and we found we did a lot of experience with different encoders in different project, and we think like if you can fine-tuning a purple UNet with a suitable encoder, you can improve the result quite a lot. So in this challenge, the final submission, we use the mixed vision transformer from the paper, the SEG-former. That was first designed by that paper, and we just reproduce in this model mixed vision former, and we replace the unit encoder with this vision transformer. And so in this case, we have the original unit is about 5 million parameters, and with the new encoder, which is a vision transformer, the total parameter is 5.2 millions. Yeah, so that's the total parameters of our model. So this is the visualization of this model. And as I mentioned, the encoder part was replaced. So this transformer has self attention block, and the layers of the unit is 4. And then yeah, this is the visualization of the structure. About the data augmentation, we did a lot of experiments, and first we start with the common data augmentation, like a rotation and vertical flip and horizontal flip, and we didn't increase the training data set. So the training data we're using is 4,000 images. Based on that, we randomly apply the data augmentation on single images. For example, the vertical flip, we give it a probability is 0.3. That means when before training, single image will be vertical flipped with the probability 0.3, and then we add one more augmentation that was applied in our final submission, which is dropout. So this is this idea was inspired by a paper from. So I will show the reference later, and so this dropout function can increase the segmentation results, as we found as well in this project, and we randomly cut out 4 multiply 4 pixel black box on single images with the probability 50%. So that will keep our model more generalized and don't lose a lot of points on the segmentation result on test data set. And so we also changed the final loss function. And so we are in this challenge, we are more focused on the segmentation result. So we didn't use other loss function. We just used the dice loss and also the cross entropy loss. So we put them together as our final loss function. For the training, yeah. So we did experiments with the baseline unit. So the baseline unit is with the random weight initialized, and we found that the result is not very good. And so we decided to use the pre-trained weight from ImagiNet, and that's also give us the best result. So our training parameters is you can see here is shown here. So it's about for each epoch is about 2 minutes. So in total, we trained our model is 40 minutes, over 40 minutes, and then yeah, we didn't have any data augmentation on our test data set, so it's only training data set. And then the evaluation we are using is the pixel accuracy. It's all the metrics is related with the segmentation, so we didn't use other metrics to evaluate our model. Yeah, so that's it basically is, and our final score you can see, and I would say the dice score for 2 organ in our model is not bad, but as I mentioned, the limitation of our research is that we didn't consider other metrics like distance. So I think that's our limitation. So our final score is not good as other people's, but our dice score is very it's very competitive. I would say. And yeah, that's it. Thank you, everybody.
Is there any question? No? Okay. Next one.
Hello, everyone. My name is Hong.
I will send a video from participated for his presentation. He did not he cannot participate in this presentation, so he recorded a video. I will show it.
Hello, everyone. My name is Hong Sun. I am from Zhejiang Gongsun University. Currently, a second-year graduate student. It is an honor to be involved here to introduce our group for the PSFHS challenge. Firstly, let me provide a brief overview of the challenge. The challenge provides 2D US images, along with segmentation labels for the particle superficies and facial hand. The training set consists of 4,000 images, while the test stage includes 401 and 700 testing images. However, accurately segmenting the target regions requires consideration of both the internal image information and capturing fine ground features at the region edges. This poses a significant challenge for this segmentation test. The current baseline model for segmentation is TransUNet, which is a topical encoder-decoder model. It include a powerful global information capturing module called the transformer. However, training a simple TransUNet model often struggles to optimize satisfactory segmentation results. Inspired by Provide's work, we propose a simple and efficient segmentation model as shown in the diagram. It has a more powerful encoder-decoder architecture. Firstly, we use a pre-trained ResNet filter as the backbone network to calculate local information at different scales. Then, to efficient model global information, we input the actual's spatial background pooling and the transformer to extract the fine ground features. After building the features, we use a stepwise upsampling approach to obtain the segmentation mask. We analyze the depth loss and cross-entropy loss as our loss functions, each with a weight of 0.5. Regarding the experimental setup, we random split 3,600 images for training and 400 images for testing. We applied random mutations and fluffs for that augmentation. Moreover, we applied the SGD optimizer with an initial learning rate of 0.01. In total, we trained the model for 100 built-in epochs with a base size of 8 for each iteration. We compared our masked with classical segmentation approaches including UNet and TransUNet. Our mask achieved the highest decibel and visually, our results are closer to the ground truth. In conclusion, we proposed an efficient encoder-decoder segmentation model, optimized using the desk loss and C loss. In the second testing stage of the challenge, we attained a score of 92.3%. In future research, we plan to explore constructive learning for medical imaging segmentation tasks. That's all. Thanks for your attention.
Okay, I think that is another presentation. Next one. I think next one is蔡鹏洲。
Hello. Can I speak in Chinese?
OK。
我共享一下我的屏幕。你们能看到我的屏幕吗？
可以看到。
大家好，我叫蔡鹏洲，我来自于重庆理工大学研二的一名学生。我今天分享一下我的这个方法。我使用的是双极路由注意力全 transformer 对于这个分割任务。好，主要从以下5点进行一个讲解。从介绍里面呢，现在的一些产科实践呢，就是努力的避免这个阴道分娩困难的一个问题。然后临床医生呢，主要是使用这个产钳或者是胎管进行一个精确的定位这个胎头的一个位置。传统上面呢，这个临床评估呢，胎头的位置呢，主要是依靠这个基因道这个东西嘛，然后它是非常主观的，然后是非常繁琐，并且是没有可靠性的。然后在2022年的时候呢，他们这个卢的人和周的人就提出一种深度学习框架，然后来分割这个指骨和胎头的一个位置，然后它计算的就是这个 AOP 的值，angle progression 进展角度。然后我们提出的方法叫做 BRA unit， 它是结合了 unit 的一种纯 transformer 结构，使用的是双极路由注意力。方法里面，首先我们将一张2D 的HW×C 的一张图像，将它分成S×S 的一个不同类的一个区域，然后包括了每个区域呢，每个 region 都包括了H×W×S 平方的一个特征向量，然后进行一个 linear projection 线性变换，分别得到这个 query 和 key 和 value 值。这个 WQ 和 WK 和 WV 呢，分别是对应于 query key 和 value 的线性变换权重矩阵。然后第二步就是 region to region 的一个路由，然后它首先呢，它是通过计算每个 region 里面的一个 QKV 的一个均值，然后用这个分别得到 QR 和 KR， 然后再用 QR 和 KR 乘以 KR 的转折，再得到一个 AR。在其中呢，这个 AR 里面的每一个实体呢，都代表着2个 region 之间的一个语义特征相似度，然后分这个 QR 和 KR。它的大小是 S平方乘 C 的，这个 AR 呢是 S平方乘 S 平方的。然后第二步采用Top K 的操作，对这个得到一个路由索引矩阵，就是这个 IR。根据这个 AR 呢，用 Top K 操作得到 IR。在这个 IR 里面呢，第 I 行就包括了第 I 个区域最相关的前 K 个索引的最相关的前K 个区域的一个索引，这个 IR 是属于大小呢是 S 平方乘 K 的。好，第三步就是这个 region to region 的一个 rotation， 它首先根据这个第二步的 region to region 的一个得到了一个 IR， 然后 gather 操作收集到这个 KG 和 VG， 然后再进行一个 softmax 以及 VG 的一个相乘，再用 LCE 做一个求和。这右边这个图呢，就是说也就是 token to token 注意力的一个过程。首先它是比如说我们这个绿色的里面我这里是分成了图上画的是四个S 等于4，那么就有16个 region， 然后每个区域里面这个绿色部分呢得 Q 也有4个，然后这3个部分呢这3个蓝色的部分也就是 K， 可以通过 gather 操作呢得到一个 KG 和 VG， 分别用 Q 和 KG 的转置呢进行一个矩阵乘法以及 max 得到一个 A， 然后 A 去乘一个 VG， 然后再加上一个 LCE， 这个 LCE 呢是一个全局上下局部上下文一个增强的一个范式，在这个 new 里也可以下去了解一下。然后这个 LCE 呢主要是用的是卷积和大小为5×5的一个主深度卷积来参数化的。然后这是它的一个算法的一个 ERA 的一个算法的一个整体流程，就是说先区块化、区域化，然后进行一个线性变换。第二步呢就是对这 QK 进行一个除均值，然后计算得到一个AR 之后再用 TOPK 的操作去选取每个区域最相关的那几个区域，然后再用第3步呢用 token to token 的操作呢，然后得到一个 KG 和 VG， 最后再算它的注意力。然后我们的方法的一个架构呢，就是基于这个双擎路约注意力搭建的一个 unit 一个形状的。从这个左边在 encoder 里面，我们通过这个 path merging 操作进行一个下采样，使它的一个通道数增倍增加以及分辨率减少。然后当图像里面，然后在这个解码器里面呢，我们使用了patch expanding 来恢复它的一个分辨率和减倍它的一个通流数。然后在右边这个地图呢，就是它的一个 BI former 的一个 block， 然后它这个3×3的一个主深度卷积呢，它可以隐式的编码它的一个相对位置信息，然后再经过linear normal 以及 BI former 这个双擎路约注意力以及和这个 LN 以及 MLP， 这个就是BI former 的一个 block 的一个详细的一个公式化。然后这个 ZL 减 E hat 呢和是主深度卷积前面的一个主深度卷积一个输出，这个 ZL hat 呢是经过双擎路约注意力得到一个输出， ZL 呢是整个 block 得到一个最终的一个输出。实验部分呢，我们实验是基于Python 3.4以及 2.0， 我们的实验是在一个3060 钛8级显存上面做的。然后我们使用 ADAM 优化器优化我们的模型，然后数据增强呢，我们使用了翻转旋转来增强数据的一个多样性。在实验里面，我们损失函数呢使用的是交叉上以及那个投掷损失的一个价值平均和。然后在这个 attention head 呢，在注意力投射上面呢，我们的每个 stage 呢采用的是2、4、8、16，而在TOPK 呢 TOPK 的操作呢选的是4、8、16以及 FIR 呢，也就是在 bottleneck 里面呢，它是分辨率是不会变的，也就是说它是可以不用这个双级路约注意力了，它就可以用全局的注意力，因为我的 region 是8×8的，也是最后分辨率也就是8×8，所以就不用这个注意。然后我们的这个网络呢是从头开始训练的，因为开始的测试集呢是没有公开的，然后我就随机的划分了400个 case 作为一个验证集，然后再用这个平均投掷系数以及好斯托夫距离评估了我们的一个模型。这左边这个呢就是我们当时的一个结果，它的一个平均投掷系数可以达到96.59%，以及好斯托夫距离呢可以是2.19，这个直固的一个 平均投球系数是95.42，以及 FHS 是97.76。这右下都是它的一个可视化曲线。然后这是第2阶段的一个结果，我们的一个最终一个 score 呢是89.74。然后结论就是我们提出了基于这个 Bi-former block 呢这一种纯 transformer 流行 encoder 结构。然后我们的论文在这个 arXiv 上面，然后这个 GitHub 呢我们也上传了我们的代码。好，谢谢大家，我的分享到此结束。
Is there any question? OK， 你结束一下共享。需要你结束一下共享，可以听到吗 ？OK， thank you everyone. Is there any presentations? If not, we will give a summarize about our challenge. Thank you everyone to participated in our challenge and give our good presentation about their methods. There are 7 players in our presentation from the fourth player to 7th. For this challenges, we have 2 tasks. One is the segmentation, another one is the measurement about the biometrics. In these challenges included about 1,000 plus patients, about 5,000 images. There are about awards for winners, about 10,000 RMBs. In this challenges included 2 phases, the first phase and the second phase. At the phase 1, there are about 179 submissions, but at the phase 2, it's about 25 submissions. According the above equations, we get the score. We also give all the values about everyone's methods. From the journal group, they get the good final score and the good angle of progression score about the 6.48. But at the most of the other scores, the second players get the good result, except the ASD plus PS. This one, the third players gets a good result. At the second phase, there are only 9 submissions, but only the 8 players win the award. So next step, all the people should give the information about their names, their supervisors, and all the people's emails, and the document about their methods, and the original code. We can say the first one and the second one, the most of the informations were completed, but from the third to 7th, most of the code are private or not can reproduce their methods. So we hope all the people's next step provided their personal information about the participants and their supervisors about the name, email, affiliations, and the winner's bank information about the account name, account number, and the account opening bank. According to this information, we will give the cash word. The first one is about the 3,000 RMB. The second one is 2,000. The third one is 1,000. 4 to 7 each will give the 500. Yeah, but the prerequisite for receive this reward is the code that can reproduce the result, methods decryption, and the related communication information. Everyone should send the above information to my email address before next week. If you do not submit this information, so maybe we cannot give you the cash reward. Is there anyone have questions about this one? If you have any questions, you can send an email to me. So this is all challenging. Thank you, everyone. That's all.
I have a question.
Okay.
Thank you
I
for
wonder how
organizing. Yeah.
Okay.
Maybe
first.
one by one. Yeah.
Okay.
Marwan, you can go ahead. Yeah.
Okay, thank you. How did you calculate the dice PS in the last slide, if I may ask?
I do not hear clearly. Can you say it slowly?
I'm asking, how did you calculate the dice PS in the last slide?
SPS. This one?
Yes, the dice PS, that is 88.81. How did you calculate it?
Because all these values based on this equation. If we know more that if there has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If we know the 10, we can infer it as another one. So we can get the if we do not give the result in your slices, we can calculate it based on this score and get this result. Yeah.
Thank you. But
Okay.
however, the columns like the 11 matrix, I would say, doesn't satisfy the score equation. When I put them on this score, the score is different. there's an error, I think, in the 2 decimal places following, like the precision of the score. So I think I sent you the correct ranking, and I didn't have a reply since then. So I'm sure you cannot use a score that is not precise or incorrect to get a value, like, you know. So if these 11 values doesn't give this score, you cannot use this score to calculate another value, no?
I agree with your notation, because every computer, they have the process of the every number, but we want to summarize it all challenging, so we can only use this way to solve all the data. Maybe some values do not vary calculatedly, but they roughly this is roughly their values. Yeah.
Yes, but when you use the accurate values coming out from Grand Challenge, you can compute the score fairly, I would say, you know?
Yeah.
So, and I think it's like, if I'm a reviewer for this paper and I saw this dice PS and I cannot actually achieve the score coming from the aggregates, I would be questioning how did the score equation you came up with? And that's it.
About this equations, I just asked one of my students calculated about the exactly the code to compute these values. Maybe I can if we submitted all papers, I can I can share all the code with everyone, and as testing images. I think maybe next year,
Yes.
April
I think,
year of the next year.
Yeah, I think like having the source code, we can check this. Thank you.
Okay. Yeah. Any question? If no, thank you everyone. Be remember provided all this information before next week. If you cannot provide this information to me, we cannot give you the cash reward. Yeah. So thank you everyone. See
Thank
you. If you have any questions, you can contact with me.
All right. See you, everybody. Thank you.
See
Thank you. Bye bye.
Bye.
See you soon.